Paradoxical patterns. People don't talk about this one, but unless they see it. I've been poked a few times over the years. Actually, this is how I got to know Chaffin's advisor, who's like this. It was John. Anyway, that got me interested in this. Kind of pointed out, how can this happen? Anyway, it's you can get these paradoxical patterns with this thing called statistical. Paradoxical patterns due to statistical suppression. I like the alliteration of that. Let's just kind of see what I mean by this. How do you get something paradoxical in this? Let's say I'm looking at interventions, and I want to look at the effect of some therapy on delinquent behavior. And I got two predictors. One is the number of sessions of therapy the kid has. More therapy should make their behavior go down. And I'm also looking at the level of family conflict. Trust me, as someone who was a clinical psychologist in training, my PhD is in child clinical psychology, you see issues that as things seem to be working, that the kid gets into therapy, but family conflict can actually accelerate as the family's in therapy. It happens sometimes. So I want to also look at family conflict. And I want to look at the effect of the treatment in relation to family conflict. So from a Venn diagram, we can look at, okay, here's treatment. Here's the R squared. We're going way back to whatever, weeks and weeks ago. Here's the R squared between family treatment, between the treatment and delinquency. And here's the effect for the family conflict. And you can see that treatment is, related to delinquency. And treatments, there's some overlap with family conflict and treatment as well. And then there's this unique bit over here of the treatment effect that's unrelated to family conflict. So you can think of the total R squared as A and B. The semi-partial, which is, remember the semi-partial squared, that's the unique effect. That's the variance that's uniquely related to just that variable. So it's the semi-partial squared. The semi-partial squared for treatment, treatment's unique effect is A. So the question is, can A ever be bigger? So can the unique effect ever be bigger than the total effect? Think about that. That's like I'm giving you I'm asking, can a piece of pie, a slice of pie, ever be bigger than the total pie? And in fact, it can. That's what's kind of crazy with suppression. It is possible, even though this is A plus B, it's possible that A is bigger than A plus B. And remember, these are squared values. So it's not because B is negative. It's because they're squared values. It may seem impossible that you get the unique effect greater than the total effect. But it may help if you think about R squared as kind of a net effect in this case. It also, I think, just inherently reflects some of the problems with Venn diagrams. That, and kind of just a limitation with them. But it's handy. I want to avoid the term, you'll see people will sometimes talk about a suppressor variable. But the kind of one variable is suppressing the effect. But I personally like to talk about in terms of suppression as a phenomena. And you might think, gosh, this seems, will this ever happen? Well, I think if you're anyone interested in intervention, whether it's in school or whatever, this is very relevant. I'm sure we see it all the time and people don't recognize it. The evidence that you're having suppression could be that the semi-partial is greater than the zero-order correlation. In other words, that's just the zero-order correlation. It's a simple correlation. If the unique effect is bigger than the correlation, you've got suppression. Actually, after writing this up, I think I'm getting my books mixed up. I don't think Keith goes into this, but you'll see people talk about this as involving noise, which is where I think it got some of the initial attention, was in some skill assessments. I think it might, actually, I should need to research this. I think it was like some Army ability tests that they figured out that they saw this and they were able to use it as a way of better identifying someone's true abilities. And you could kind of purify, you could pull out some of the noise in one predictor and come up with a more pure relationship between the other predictor and the outcome. But I think in terms of behavioral stuff that in education or behavioral sciences we deal with, I think we often, when we see it, I think it's often a case of where we have a homeostatic relationship. And what I mean by that is a relationship where there are things driving something to not move, where that you're kind of in you're trying to balance out to a point. Well, we'll see in just a sec. Okay. Kind of here, if we look at this, let's say I just look at treatment. Here's some examples. So I made some data to illustrate this. And I first start, I'm looking at delinquency. I enter treatment, and the R squared is 0. Treatment has no effect on the outcome. Now, I think in the real world, that would be really, really depressing. My treatment is doing nothing to help the kid. You can't get less of an effect than 0. The regression coefficient, the R squared 0, the regression coefficient 0, the t is 0, the p-value is 1. No effect. You can't get less. But now, let's say I look at conflict all on its own. In the first model, I've kind of highlighted here. So that's when it's just conflict in the model. Conflict, family conflict, has an R squared of 0.498. So the total effect of family conflict with delinquency, which makes sense, is very big. The regression coefficient, when I'm in this model where I just have conflict, the regression coefficient is 0.996. The t-value is very big, very significant. More conflict in the family, more delinquency in the kid. That makes complete sense, right? More conflict, more behavior problems in the kid. But what happens to treatment when we control for conflict? So now we add treatment after conflict. We saw treatment had no effect when it was entered first. But controlling for conflict, treatment, the total R squared is now 99.3% or 0.993. Treatment had an R squared of 0 on its own, but now it adds an additional 0.4 to the R squared. It accounts for 49% of the variance. On its own, it accounts for 0% of the variance. Controlling in delinquency, but somehow magically almost, after we control for conflict, it accounts for almost half the variance. It's crazy. How does that work? If we look at the regression coefficient, we see treatment has, the regression coefficient is now negative 0.993. So more treatment, the delinquency goes down, the treatment's working. But remember, when we didn't control for conflict, the treatment had no effect. But now, yeah, more treatment, kid's getting better. Very big t-score, very significant. The effect for conflict is still very significant. What's really kind of crazy, remember we can square the semi-partials and they tell us the unique effect of each variable. Well, the semi-partial for conflict is almost 1. 0.99 squared is almost 1. The semi-partial for treatment squared is negative 0.7 squared is 0.5. If we add up these two unique effects, so you remember the Venn diagram, these are the parts that don't overlap. They account for right about 150% of the variance, which is, you can't account for 150% of the variance. So how is it that their unique effects can account for more variance than there is in the variable? Crazy. The correlation matrix can help us see that. And if we look at the correlation, the correlation between, this is kind of an odd layout, I apologize for it. The correlation between conflict and treatment is 0.7. The correlation between conflict, there's the p-value. So the correlation between the treatment and conflict is 0.7. So treatment, more treatment is leading to more conflict in the family, or more family conflict. What you end up having is something like this. That treatment leads to more conflict. Conflict leads to more delinquency. Treatment, that's the indirect effect of treatment. The direct effect of treatment, though, is very, as we'd expect, more treatment, less delinquency. You've got kind of opposing processes going on at the same time. It's not that the treatment's not helping the kid. It's that the treatment's helping the kid, but at the same time, the family is pushing back on it. It's kind of the clinical psych side of it, or kind of the clinical psych example of this sort of thing, which I think happens. That your intervention, and people will say this all the time, I know my intervention's helping the kid. Why am I not seeing it? I think part of what you might see are these sorts of things. You're in a we're often working in these complex worlds. And that you are detecting, you're able to see, I know it's helping the kid because you are, clinically, you're seeing it's having this good effect. But there's other things that are now still my hand just locked up and hurt, but it's all better now. So you have a negative effect this way, and this is a positive, in terms of negatives, it's a positive effect, but you know what I mean, a negative association. But then this is positive and a positive, so you got the negative one way, and then the two positives, they're balancing each other out. And so in the end, when you look at treatment all on its own, nothing. But you partial out this effect, and you partial out this, and you're left being able to see that big negative effect. And when you look at the direct effects, you've got that big positive effect and that big negative effect. So it's interesting. That's what I mean by homeostasis. That we often, I think, are dealing with these things, interventions, that if this is the effects may not be as strong as we would like, but this sort of modeling is a way of being able to detect it. Instead of just at the end saying, holy cow, there's nothing going on. I did this intervention, the correlation 0. How depressing, which would be depressing. Kind of looking at it a little bit more, thinking of this kind of from a path sort of process sort of approach can help you to understand that it's not that simple. There's more going on here than you might think. And again, I think we see this a lot, this sort of a pattern. Okay, let's stop there. We'll talk about power analysis next week and then kind of move on.